Introduction: A fever that changed the world. In the searing summer of 1793, the streets of Philadelphia became an apocalyptic tableau. Men, women, and children fell ill in waves, their skin turning a sickly yellow, their bodies racked by fever. Some vomited black bile, gasping for breath as death approached. Corpses piled up in the sweltering heat, forcing panicked citizens to flee the city. Within months, the bustling U.S. capital was a ghost town, and over 5,000 people, 1/10 of the population, lay dead. It was called the Yellow Jack, the Black Vomit, the American Plague. But Philadelphia was only the latest chapter in a story that stretched back centuries. Long before it ravaged the New World, yellow fever had stalked the jungles of Africa, a shadowy killer that eluded human understanding. By the time it boarded slave ships bound for the Americas, the virus was poised to alter the course of empires, shape the destiny of nations, and test the limits of human ingenuity. This is the story of yellow fever, a disease that defied science for centuries, lurking in the wings of a mosquito too small to notice, yet powerful enough to bring cities and armies to their knees. It is a story of hubris and discovery, of devastating failures and transformative breakthroughs. From the frantic streets of 18th century Havana to the jungles of Brazil and the laboratories of Rockefeller scientists, yellow fever has left its mark on every continent it has touched. It is also a story of resilience. For every mysterious death, there was a question. For every failed hypothesis, a new idea. And for every epidemic, an enduring lesson about the interplay between humans, nature, and disease. Yellow fever may not be the pandemic of our time, but its story is as relevant as ever. In an era of climate change, urbanization, and global connectivity, the lessons learned from yellow fever's triumphs and tragedies offer a blueprint for addressing the infectious diseases of the future. This book unravels the layers of yellow fever's history, from its grim beginnings to the scientific breakthroughs that brought it under control, and the challenges that still lie ahead. It is a story of science, survival, and the fragile balance between humanity and the natural world. Welcome to the fever that changed the world. Chapter 1. The fever that painted the world. Yellow. The first whispers of yellow fever likely began in the dense tropical forests of Africa, where the virus coexisted with non-human primates and mosquitoes long before humans became part of its deadly dance. For centuries, it simmered silently in isolated ecological pockets. But with the rise of transatlantic trade in the 16th century, the virus hitched a ride across oceans, ushering in an era of pandemics that would shape the histories of continents. The arrival. Yellow fever entered the Americas through the brutal currents of the transatlantic slave trade. The African Aedes aegypti mosquito, the vector of the disease, and infected humans traveled aboard ships bound for the Caribbean, Central, and South America. This small, seemingly insignificant mosquito became a harbinger of devastation. In its new environment, yellow fever found fertile ground. The humid tropics, burgeoning port cities, and dense, unsanitary living conditions created a perfect storm. By the early 1600s, the virus had established itself as a persistent threat in the Americas, causing sporadic outbreaks that killed thousands. Missionaries and colonial officials began documenting strange episodes of high fever, jaundice, and fatal hemorrhages, often calling it the black vomit disease because of the dark, clotted blood ejected by its victims. Jesuit priests described scenes of entire plantations falling silent, with bodies stacked in makeshift graves. Philadelphia, 1793, a nation paralyzed. Yellow fever's most infamous outbreak in early America struck Philadelphia in the summer of 1793. The city, then the U.S. capital, was teeming with trade and immigrants. It was also unprepared for the tiny invader that thrived in water barrels and stagnant pools around the docks. The epidemic began subtly. A few fevers, a handful of deaths, but within weeks it escalated into a full-scale disaster. People turned jaundiced, vomited black fluid, and succumbed to agonizing deaths. Fear gripped the city. By the end of the year, over 5,000 people, 10% of Philadelphia's population, were dead. Physician Benjamin Rush, one of the outbreak's most prominent figures, chronicled the suffering. His treatments, however, became part of the story's tragedy. Believing the disease stemmed from bad air or miasmas, Rush relied on aggressive bloodletting and purging. His interventions likely worsened outcomes for many patients, but his detailed records would prove invaluable to future scientists. The mystery of transmission. For centuries, yellow fever's transmission baffled physicians. The prevailing theories ranged from bad air, miasmas, to person-to-person contact. Yet, neither explanation accounted for its erratic behavior, how it could devastate one town and leave another untouched, or disappear during cooler seasons. The first hints of a breakthrough came in the late 19th century. In Havana, a Cuban physician named Carlos Finley observed patterns in yellow fever outbreaks and hypothesized a link to mosquitoes. His experiments were meticulous but unconvincing to his peers, who clung to older theories. It would take decades, and a team led by U.S. Army physician Walter Reed for Finley's hypothesis to be confirmed. Reed's experiments in 1900 showed conclusively that the Aedes aegypti mosquito was the primary vector for yellow fever. Volunteers exposed to infected mosquitoes developed the disease, while those protected from mosquito bites did not. This discovery transformed the understanding of the disease, shifting focus from direct contagion to vector control. The science of yellow fever. Yellow fever is caused by a virus in the Flaviviridae family, named for the Latin word flavus, meaning yellow, after the jaundice it causes. Its genetic material is a single strand of RNA, a compact instruction manual for the virus to invade cells and replicate. Once inside the human body, the virus targets liver cells, causing inflammation and the telltale yellowing of the skin. The virus is transmitted in two main cycles. 1. Urban cycle. Humans and Aedes aegypti mosquitoes in cities fuel rapid outbreaks. 2. Sylvatic cycle. Non-human primates and forest-dwelling mosquitoes maintain the virus in jungle environments, making eradication impossible. The disease progresses in two phases. Acute phase, fever, chills, muscle pain, and nausea. Toxic phase, jaundice, internal bleeding, kidney failure, and death. Mortality in severe cases exceeds 50%. Understanding this duality of cycles and symptoms would later become critical for controlling outbreaks. A disease that shaped history. Yellow fever's impact extended beyond the human body. It shaped the destinies of nations. Napoleon's dreams of a new world empire collapsed when yellow fever decimated French troops sent to quell the Haitian Revolution in 1802. Haiti's independence, a seismic event in global history, was indirectly fueled by the virus. Later, yellow fever would threaten the construction of the Panama Canal, halting progress until effective mosquito control measures were implemented. Its outbreaks disrupted trade, migration, and urbanization, leaving indelible marks on the Americas, Africa, and beyond. Chapter 2. The Mosquito and the Mystery. By the dawn of the 20th century, yellow fever had claimed millions of lives, crippled economies, and devastated cities. It was a disease that seemed unstoppable, a phantom that struck without warning and disappeared just as mysteriously. Yet, its secret lay not in the air or contaminated water, but in the tiny, buzzing wings of a mosquito. This chapter delves into the long journey toward uncovering this truth, the dogged persistence of a few brilliant minds, and the pivotal experiments that turned the tide. The problem of pattern. Yellow fever's unpredictable nature left scientists baffled. Why did it strike coastal cities like Havana with regularity, but spare others inland? Why did outbreaks subside in winter? Theories abounded, but none fit the observations. The miasma theory, dominant for centuries, blamed foul-smelling air and decaying matter. While it explained urban outbreaks, it failed to account for rural cases. Some proposed direct contagion, the idea that yellow fever spread through contact with infected individuals. But this theory faltered in explaining why doctors and nurses rarely contracted the disease while handling patients. Despite the mounting contradictions, these theories persisted because no alternative had been proven. Carlos Finley's revolutionary hypothesis. In 1881, Cuban physician Carlos Finley proposed a daring idea. Mosquitoes were the vectors of yellow fever. Drawing from his observations in Havana, Finley noted that outbreaks occurred in areas with stagnant water and high mosquito populations. He reasoned that the Aedes aegypti mosquito, common in tropical cities, might play a role in transmitting the disease. Finley's hypothesis was revolutionary, but his experiments failed to convince the scientific community. He struggled to produce consistent results, as the methods for proving mosquito transmission were still rudimentary. His findings were dismissed as speculative, and for decades his work languished in obscurity. The turning point: Walter Reed and the U.S. Army. The tide began to shift during the Spanish-American War, 1898. The United States, controlling territories like Cuba and Puerto Rico, faced frequent yellow fever outbreaks that threatened military operations. The U.S. Army Medical Corps, tasked with controlling the disease, turned to Carlos Finley's mosquito theory for answers. Walter Reed, a U.S. Army physician, led a team to investigate. Between 1900 and 1901, in what became one of the most famous series of experiments in medical history, Reed and his colleagues proved Finley's hypothesis correct. Their work, conducted in Havana, was as dangerous as it was groundbreaking. The experiments. The team allowed mosquitoes that had bitten yellow fever patients to bite healthy volunteers. Those exposed to mosquito bites developed yellow fever, while those protected from mosquitoes did not. Volunteers included members of Reed's own team, demonstrating the courage and desperation of their efforts. The experiments also established the extrinsic incubation period, showing that mosquitoes could only transmit the virus after a period of 10-12 days. Ethical considerations. Reed's experiments relied on informed consent, a relatively novel concept at the time. Volunteers were paid and made aware of the risks, a stark contrast to many other studies of the era. The vector is revealed. Reed's findings proved decisive. The Aedes aegypti mosquito was confirmed as the primary vector of yellow fever, finally unmasking the mechanism behind its transmission. This breakthrough laid the foundation for controlling the disease by targeting mosquitoes. Immediate impact. In Havana, mosquito control measures were rapidly implemented. Stagnant water was drained, and insecticides were used to kill larvae. Within months, the city's yellow fever cases plummeted. The findings were replicated in other regions, transforming public health strategies worldwide. The reluctant hero, Carlos Finley. For decades, Finley's contributions were overlooked. Though Walter Reed credited Finley's work in his reports, the international scientific community was slow to recognize the Cuban doctor's role. It wasn't until years after Reed's death that Finley received widespread acknowledgement as the originator of the mosquito hypothesis. Biology of the killer. the role of Aedes aegypti. The Aedes aegypti mosquito, deceptively small and seemingly harmless, is perfectly adapted to spread yellow fever. Habitat. It thrives in urban areas, breeding in small collections of stagnant water like cisterns, barrels, and even discarded tins. Behavior. Unlike many mosquitoes, Aedes aegypti is a day biter, making it harder to avoid. Its preference for human blood increases its efficiency as a disease vector. Transmission. Once infected, a mosquito can transmit yellow fever for the rest of its life. Understanding the mosquito's biology was key to devising control measures. By disrupting its life cycle, eliminating breeding grounds, and using insecticides, public health officials could break the chain of transmission. The fight against the mosquito. The discovery of the mosquito's role turned yellow fever from an unsolvable mystery into a manageable threat. Public health campaigns in the early 20th century focused on eradication of breeding grounds. Cities drained stagnant water, sealed cisterns, and improved sanitation. Education campaigns. Residents were taught to cover water containers and eliminate standing water. Use of insecticides. Early chemical agents, though crude, proved effective in reducing mosquito populations. The success of these campaigns in Havana demonstrated that controlling the mosquito could control the disease, a principle that would shape public health efforts for decades. Legacy of the discovery. The identification of the Aedes aegypti mosquito as the vector for yellow fever is one of the great triumphs of science. It marked a turning point not just for the disease, but for the broader field of epidemiology. The experiments in Havana demonstrated the power of controlled scientific inquiry and set a precedent for future research into vector-borne diseases like malaria and dengue. Carlos Finley's vision, Walter Reed's courage, and the dedication of countless public health workers transformed yellow fever from an uncontrollable scourge into a manageable threat. Yet, as later chapters will show, this was only the beginning. Chapter 3. The Vaccine That Changed Everything. By the early 20th century, yellow fever was no longer a complete enigma. The mosquito vector had been identified, and control measures were proving effective in curbing outbreaks. Yet, the disease persisted in regions where Aedes aegypti thrived. Its unpredictable sylvatic cycle meant that eradication was out of reach. The world needed something more. Something that would shield individuals from the virus itself. The answer lay in the groundbreaking development of the yellow fever vaccine, a feat of science that would save millions of lives, a deadly challenge. Despite the success of mosquito control campaigns in urban areas, yellow fever outbreaks continued to erupt. Rural regions, where the sylvatic cycle persisted, remained a constant source of infection. Non-human primates acted as reservoirs, while forest-dwelling mosquitoes like Haemococcus species spread the virus to humans venturing into jungle areas. In these settings, mosquito control was impractical and outbreaks seemed inevitable. Moreover, yellow fever re-emerged in cities whenever mosquito control efforts lapsed. This pattern was evident during the devastating outbreaks in Africa and South America throughout the 1920s and 1930s. The disease continued to paralyze communities, kill thousands, and stifle economic development. It became clear that controlling mosquitoes was not enough. A vaccine was essential. The Rockefeller Foundation steps in. The Rockefeller Foundation, already a key player in yellow fever research and control, recognized the urgency of finding a vaccine. In the 1920s, they established dedicated research programs in Africa and South America, recruiting some of the brightest minds in virology and immunology. Their goal was ambitious: to develop a vaccine that was safe, effective, and scalable. In 1927, a major breakthrough occurred when the yellow fever virus was successfully isolated by Adrian Stokes in West Africa. This enabled scientists to study the virus in detail and begin the arduous process of vaccine development, the road to the 17D vaccine. Max Thiele, a South African virologist working with the Rockefeller Foundation, led the effort to create a vaccine. Using a strain of the yellow fever virus isolated from a patient in Ghana, Thiele began a series of experiments aimed at weakening or attenuating the virus so it could stimulate immunity without causing disease. Passaging through mice. Thiele repeatedly passed the virus through mice, causing it to lose its virulence for humans while retaining its ability to trigger an immune response. Adaptation to chicken embryos. To ensure safety and scalability, Thiele adapted the virus to grow in chicken embryos, a process that further attenuated its virulence. By 1937, Thiele had developed the 17D vaccine, named for the strain of virus used. It was tested extensively in humans and showed remarkable results. Recipients developed strong immunity with minimal side effects. The global rollout. Thieler's vaccine quickly became the cornerstone of yellow fever control efforts. Over the next 2 decades, mass vaccination campaigns transformed the fight against the disease. 1. Africa. Large-scale vaccination efforts targeted high-risk areas, significantly reducing the incidence of urban yellow fever. 2. South America. In jungle regions, vaccination campaigns were paired with mosquito control to protect vulnerable populations. 3. Military use. During World War II, Allied forces used the vaccine to protect troops stationed in tropical regions, preventing potentially catastrophic outbreaks. The 17D vaccine's impact was immediate and profound. For the first time, yellow fever was brought under control on a global scale. The science of immunity. The 17D vaccine works by introducing an attenuated form of the yellow fever virus into the body. This weakened virus cannot cause disease, but triggers the immune system to produce a robust response. Key elements of its effectiveness include long-lasting immunity. A single dose of the vaccine provides lifelong protection for most individuals. Safety profile. The vaccine's safety was unparalleled for its time, with only rare adverse events reported. Understanding why the vaccine works so well lies in the biology of the virus. Yellow fever is a simple virus with a highly conserved genome, meaning it doesn't mutate as rapidly as other viruses like influenza. This stability allows a single vaccine to remain effective across time and geographic regions. Challenges and failures. While the 17D vaccine was a triumph, its rollout was not without challenges. Cold chain requirements. The vaccine needed to be stored at low temperatures, making distribution difficult in remote or resource-poor areas. Vaccine-associated adverse events. In rare cases, the vaccine caused severe side effects, including yellow fever-like symptoms. Known as vaccine-associated viscerotropic disease, VAVD, these events underscored the need for careful screening of recipients. Additionally, the vaccine could not address the sylvatic cycle. As long as yellow fever persisted in non-human primates, the risk of outbreaks remained. The legacy of Max Thiele. In 1951, Max Thiele received the Nobel Prize in Physiology or Medicine for his work on the yellow fever vaccine. He remains one of the few virologists to receive this honor, and his achievement is considered one of the greatest successes in vaccine history. Thieler's work also set a precedent for modern vaccine development. Techniques used in the creation of the 17D vaccine would later inspire efforts to combat other diseases, including polio and measles. A disease on the brink, by the mid-20th century, yellow fever seemed to be on the verge of eradication. Vaccination campaigns had drastically reduced cases in endemic regions, and mosquito control measures kept urban outbreaks at bay. Yet, as later chapters will show, yellow fever's sylvatic cycle and the complexities of maintaining global vaccination coverage meant the disease would never fully disappear. Chapter 4. The Jungle's Secret, the Sylvatic Cycle. The 20th century battle against yellow fever unfolded in two acts. The first act played out in cities, where urban outbreaks were tamed through mosquito control and vaccination campaigns. But the second act, set deep in the jungles of Africa and South America, revealed a far more complex enemy. Here, yellow fever hid in the sylvatic cycle, an ecological loop that made the virus impossible to eradicate. This chapter explores the discovery of the sylvatic cycle, the role of non-human primates, and the ecological challenges that keep yellow fever alive. An unexpected reservoir. Yellow fever had long been thought of as an urban disease, primarily affecting humans and transmitted by Aedes aegypti mosquitoes. But as vaccination programs took hold and mosquito control reduced urban cases, outbreaks continued to emerge sporadically in rural areas. Investigators in the mid-20th century began to suspect that the virus was being sustained in a natural reservoir outside of human populations. In the 1930s and 1940s, field studies in Africa and South America provided the answer. Scientists discovered that non-human primates, particularly monkeys, harbored the yellow fever virus. These primates were not merely incidental hosts, they were integral to the virus's survival in the wild. The yellow fever virus could circulate indefinitely between monkeys and forest-dwelling mosquitoes, forming what is now known as the sylvatic cycle. The sylvatic cycle explained. The sylvatic cycle functions as a closed loop within jungle ecosystems. 1. Non-human primates. Monkeys are the primary reservoir of the virus. Infected monkeys often show symptoms and can die from the disease, but they can also survive and develop immunity. 2. Mosquito vectors. Forest mosquitoes, particularly species in the Hemagogus and Sabethes genera, transmit the virus between monkeys. 3. Human spillover. When humans enter these jungle environments, for logging, farming, or tourism, they risk being bitten by infected mosquitoes and contracting the virus. Unlike the urban cycle, where humans and Aedes aegypti mosquitoes are the key players, the sylvatic cycle operates independently of human populations. This ecological reality makes the virus impossible to eradicate, as it is perpetually maintained in the natural environment. Field discoveries in South America. In the 1930s, scientists with the Rockefeller Foundation conducted extensive studies in the jungles of Brazil. They trapped monkeys, collected mosquito specimens, and tested them for yellow fever. These efforts revealed that species like the red howler monkey were highly susceptible to yellow fever and often died during outbreaks. Hemagogus janthinomes, a forest-dwelling mosquito, played a critical role in transmitting the virus between monkeys and occasionally to humans. The researchers also observed that outbreaks among monkeys often preceded human cases, serving as an early warning system for potential epidemics. Lessons from Africa. Similar discoveries were made in Africa, where the virus was found to circulate among a variety of primate species and forest mosquitoes. In West Africa, studies in the 1940s and 1950s confirmed that yellow fever was endemic in forested regions, with periodic spillover into human populations. The diversity of mosquito vectors and primate hosts made controlling the sylvatic cycle far more challenging than the urban cycle. These findings helped explain why yellow fever could never be eradicated. As long as the virus had a foothold in the jungle, it could re-emerge in human populations at any time. The challenges of containment. The discovery of the sylvatic cycle posed significant challenges for public health. 1. Ecological complexity. Unlike urban outbreaks, which could be controlled through mosquito eradication and vaccination, sylvatic yellow fever was deeply embedded in natural ecosystems. Intervening in these cycles was impractical and potentially harmful to biodiversity. 2. Surveillance difficulties. Monitoring yellow fever in remote jungle areas required significant resources and expertise. The absence of human cases did not mean the virus was gone. It could be circulating silently among primates and mosquitoes. 3. Human activity. As deforestation, agriculture, and urban expansion pushed humans deeper into forested areas, the risk of spillover events increased. Logging camps and construction sites became hotspots for sylvatic yellow fever outbreaks. Modern tools for monitoring. Despite these challenges, advances in science have improved the ability to track yellow fever in sylvatic settings. Primate sentinel surveillance. Monitoring monkey populations for yellow fever outbreaks provides an early warning system for potential human cases. Genomic studies. Sequencing the yellow fever virus from infected primates and mosquitoes has helped map its transmission patterns and evolution. Remote sensing and GIS. Geographic Information Systems, GIS, and satellite imagery are used to identify high-risk areas based on environmental factors like vegetation and mosquito habitats. These tools have become essential for predicting and preventing outbreaks, particularly in regions where the sylvatic cycle is active. The ongoing threat. The sylvatic cycle ensures that yellow fever will remain a global health threat for the foreseeable future. In 2016, an outbreak in Angola spread to cities and sparked fears of a global epidemic. Genetic analysis later revealed that the virus originated in the jungle, underscoring the persistence of the sylvatic reservoir. Efforts to control yellow fever now rely on a combination of vaccination, surveillance, and education. While the urban cycle can be managed through targeted interventions, the sylvatic cycle requires long-term vigilance and an understanding of the ecological factors that sustain the virus. Conclusion. The discovery of the sylvatic cycle marked a turning point in the fight against yellow fever. It revealed the virus's deep entanglement with the natural world and highlighted the limits of eradication efforts. Instead, the goal shifted to containment, protecting human populations while respecting the ecological balance of the jungle. This delicate interplay between science, public health, and nature remains at the heart of the yellow fever story. Chapter 5. The Resurgence and the Global Response. For much of the 20th century, yellow fever seemed to be a problem of the past in many parts of the world. Vaccination campaigns and mosquito control measures reduced urban outbreaks, and the global focus shifted to other diseases. However, the turn of the 21st century saw a resurgence of yellow fever in both Africa and South America, driven by environmental, social, and political factors. This chapter explores the modern challenges of yellow fever outbreaks, the global response, and the ongoing battle to prevent a pandemic. The return of yellow fever. Yellow fever's resurgence in the late 20th and early 21st centuries was not unexpected. Public health experts warned that gaps in vaccination coverage, urbanization, and deforestation could fuel new outbreaks. These fears were realized in a series of epidemics that underscored the fragile nature of disease control. Angola and the Democratic Republic of Congo, 2015-2016. In late 2015, Angola reported its first yellow fever outbreak in decades. The virus quickly spread, infecting thousands and killing hundreds. The outbreak spilled into neighboring Democratic Republic of Congo, DRC, and sparked fears of an international epidemic. Key factors that contributed to this outbreak included urbanization. Rapid population growth in cities like Luanda created ideal conditions for Aedes aegypti mosquitoes to thrive. Gaps in vaccination. Many urban residents had not received the yellow fever vaccine, leaving them vulnerable. Global connectivity. Travelers carried the virus to other countries, including China, raising concerns about yellow fever's spread to non-endemic regions. The outbreak overwhelmed vaccine supplies. The World Health Organization, WHO, coordinated an emergency response, including mass vaccination campaigns using fractional doses, 1/5 of the standard dose, to stretch limited supplies. This innovative strategy successfully curbed the outbreak, but it highlighted the precariousness of global vaccine stockpiles. Urbanization and the threat of global spread. Yellow fever thrives in urban environments where dense populations provide ample hosts for Aedes aegypti mosquitoes. Modern urbanization trends, particularly in Africa and South America, have created cities that are both densely populated and poorly equipped to handle outbreaks. Brazil's outbreaks, 2016-2019. Brazil experienced significant yellow fever outbreaks beginning in 2016. Initially limited to rural areas, the virus spread to urban centers, including Sao Paulo and Rio de Janeiro, threatening millions. Role of the sylvatic cycle. The outbreaks originated in jungle regions but moved closer to cities as human activity encroached on forest habitats. Vaccination challenges. Brazil's vaccination campaigns faced logistical hurdles, including reaching rural populations and combating vaccine hesitancy. Brazil's outbreaks underscored the difficulty of containing yellow fever when both urban and sylvatic cycles converge. Climate change and yellow fever. Climate change has emerged as a critical factor in yellow fever's resurgence. Rising temperatures and altered rainfall patterns have expanded the habitats of Aedes aegypti and forest mosquitoes like Haemagogus. Areas that were once too cool for the virus and its vectors are now at risk. Expanding risk zones. Africa. Warming temperatures have pushed mosquito habitats into new regions, increasing yellow fever risk in previously unaffected areas. Asia. Although yellow fever is not endemic to Asia, the presence of Aedes aegypti and global travel create the potential for outbreaks. The global vaccine supply challenge. One of the greatest obstacles in combating yellow fever is ensuring an adequate supply of vaccines. The 17D vaccine remains the cornerstone of prevention, but its production is complex and limited to a few facilities worldwide. Vaccine shortages. Outbreaks like those in Angola and Brazil have exposed the vulnerabilities of relying on a finite vaccine supply. In emergency situations, fractional dosing has proven effective, but it is not a long-term solution. Stockpile initiatives. The WHO and partners, including Gavi, the Vaccine Alliance, have established an emergency vaccine stockpile to respond to outbreaks. This initiative has been critical in preventing global epidemics, but requires ongoing funding and coordination. The role of genomics in modern surveillance. Advances in genomic sequencing have revolutionized the understanding of yellow fever outbreaks. By analyzing the virus's genetic code, scientists can trace its origins, monitor mutations, and predict its spread. Genetic insights. During the Angola outbreak, genomic studies revealed that the virus was closely related to strains circulating in Africa, confirming that the outbreak originated locally. In Brazil, sequencing showed that the virus was spreading from jungle regions into urban areas, highlighting the role of the sylvatic cycle in sparking urban outbreaks. International collaboration. Yellow fever's resurgence has underscored the importance of global collaboration. No single country can tackle the disease alone, especially in an era of rapid travel and interconnected economies. Eliminate yellow fever epidemics. I strategy. Launched in 2017, the I strategy is a global initiative led by the WHO, UNICEF, and Gavi. Its goals include 1. Protecting at-risk populations through vaccination. 2. Strengthening outbreak detection and response capabilities. 3. Ensuring sustainable vaccine supplies. This strategy represents a coordinated effort to prevent yellow fever from becoming a global health crisis. The persistent threat. Despite these efforts, yellow fever remains a looming threat. The sylvatic cycle ensures the virus will never be eradicated, and the challenges of vaccination, surveillance, and climate change demand constant vigilance. The resurgence of yellow fever serves as a stark reminder of the delicate balance between humans and the natural world. Conclusion. The modern story of yellow fever is one of both progress and peril. Vaccination campaigns and global collaboration have prevented catastrophic pandemics, but the resurgence of outbreaks highlights the ongoing challenges. In a world shaped by urbanization, climate change, and global travel, yellow fever continues to test humanity's ability to adapt and respond. Chapter 6. A Blueprint for Future Epidemics. The resurgence of yellow fever offers not only a cautionary tale but also a blueprint for addressing other emerging and re-emerging infectious diseases. As a disease deeply entwined with ecological changes, human activity, and global connectivity, yellow fever serves as a microcosm of the challenges and strategies that define modern public health. This chapter explores the lessons learned from yellow fever's story and how they can inform global efforts to prepare for and respond to future epidemics. Lesson 1. The importance of vaccination. Vaccination has been the most effective tool in controlling yellow fever, but its success is contingent on sustained efforts. The global response to yellow fever highlights critical aspects of vaccine deployment, equitable access. The 17D vaccine is a marvel of science, but its availability is limited by production constraints. Ensuring equitable access requires increased investment in vaccine manufacturing capacity, collaboration with low-income countries to strengthen distribution systems, policies that prioritize high-risk populations during outbreaks, routine immunization. Yellow fever outbreaks often occur in regions where vaccination coverage has lapsed. Incorporating yellow fever vaccination into routine childhood immunization schedules ensures consistent coverage and reduces the risk of epidemics. Innovation. Advances in vaccine technology, such as thermostable vaccines that don't require cold chain storage, could revolutionize yellow fever prevention in remote areas. Lesson 2. Surveillance and early warning systems. Effective surveillance is the cornerstone of epidemic prevention. The yellow fever story demonstrates the value of early detection and rapid response. Primate sentinel programs. Monitoring primate populations for yellow fever outbreaks provides an early warning system, particularly in regions where the sylvatic cycle is active. Genomic sequencing. The use of genomic sequencing to track the evolution and spread of yellow fever virus has improved outbreak prediction and response. These methods can be applied to other vector-borne diseases, enabling proactive measures. Integration with other disease programs. Surveillance systems for yellow fever can be integrated with those for dengue, Zika, and other arboviruses, leveraging resources and improving efficiency. Lesson 3. The role of vector control. Controlling mosquito populations remains a critical component of yellow fever prevention, but it is a challenging task that requires innovative approaches. Traditional methods. Removing standing water, applying larvicides, and using insecticides have proven effective in urban areas but are difficult to sustain in rural or sylvatic settings. Genetic engineering. Recent advances in genetic engineering, such as the release of sterile or gene-edited mosquitoes, offer promising tools for controlling Aedes aegypti populations. These methods are still in experimental stages, but could transform vector control strategies. Community involvement. Engaging local communities in mosquito control efforts ensures sustainability and effectiveness. Education campaigns that teach residents how to eliminate breeding sites can reduce reliance on external interventions. Lesson 4. Addressing the impact of climate change. Climate change has expanded the geographic range of yellow fever vectors, increasing the risk of outbreaks in previously unaffected regions. Addressing this challenge requires a multidisciplinary approach. Predictive modeling. Using climate and ecological data to predict shifts in mosquito habitats allows for preemptive public health measures. These models can inform vaccination campaigns and resource allocation. Urban planning. Designing cities with proper drainage and waste management systems reduces mosquito breeding sites. Incorporating climate resilience into urban planning is essential to prevent outbreaks in growing cities. Global collaboration. Climate change is a global issue, and its impact on disease transmission requires international cooperation. Strengthening partnerships between countries and organizations ensures a unified response to emerging threats. Lesson 5. The value of global partnerships. Yellow fever's resurgence has demonstrated that no country can tackle epidemics alone. International collaboration is essential for effective disease control. The I strategy. The Eliminate Yellow Fever Epidemics I strategy provides a model for coordinated global action. By bringing together governments, nonprofits, and international organizations, the I strategy has conducted mass vaccination campaigns in high-risk areas, built stronger surveillance networks, strengthened health systems to respond to outbreaks, emergency response frameworks, rapid deployment of emergency teams and resources during outbreaks, such as those seen in Angola and Brazil, underscores the need for well-coordinated response frameworks. Learning from success. The lessons learned from yellow fever can be applied to other global health challenges, from cholera to COVID-19, emphasizing the importance of collaboration in an interconnected world. Lesson 6. Balancing human activity and ecosystems. The sylvatic cycle of yellow fever highlights the delicate balance between human activity and natural ecosystems. As humans encroach on forests and alter landscapes, they increase their exposure to zoonotic diseases, protecting biodiversity. Maintaining healthy ecosystems can reduce the risk of spillover events. Preserving forests and minimizing deforestation are essential steps in mitigating the sylvatic cycle. Sustainable development. Development projects, such as logging and agriculture, should include measures to monitor and mitigate health risks. Balancing economic growth with ecological conservation is critical for long-term health security. Looking ahead, the story of yellow fever is far from over. The virus remains a persistent threat, and its lessons resonate across the spectrum of public health. As we face new challenges, from emerging zoonotic diseases to the impacts of climate change, the strategies developed to combat yellow fever offer a roadmap for navigating the complexities of infectious disease control. A future beyond yellow fever. While eradication is unlikely, the tools to prevent yellow fever epidemics exist. The challenge lies in sustaining and adapting these efforts to a changing world. The virus may be ancient, but the fight against it is continually evolving, reflecting humanity's resilience and ingenuity. Conclusion. Yellow fever's history is a testament to both the power and limitations of human intervention. Its story reveals the interconnectedness of science, society, and the environment, offering lessons that extend far beyond a single disease. In understanding yellow fever, we gain insights into the broader battle against infectious diseases and the ever-changing relationship between humans and the natural world.